Welcome to the second talk of the morning. So following on from the talking about security APIs in general yesterday, today we're going to look specifically at the problem of designing an API to manage cryptographic keys for general services. So we're going to look in particular at a case study of what is the most widely used API for managing crypto in all sorts of applications, which is RSA PKCS 11, or the API crypto key, which is defined inside that standard. We're going to go through a whole bunch of vulnerabilities and their associated mitigations, and we're going to try and come up with a formal story of how we can configure RSA PKCS 11 in a secure way. And then finally, perhaps we're going to be so annoyed with RSA PKCS 11 that we're going to look at other alternatives, what other APIs there are out there emerging in industry standards and in academic work to try and replace this rather tricky and rather open standard. So what is the problem of key management? So here's a nice little quote from Bruce Schneier. So key management is the hardest part of cryptography and often the Achilles heel of an otherwise secure system. Okay? What do we mean by this key management problem? Well, we mean the management of the whole life cycle of a cryptographic key. Okay? So everything that happens from the creation of a key through to its destruction, the deletion of all its copies, everything in between, including how do we establish pairs of keys between entities who want to communicate, how do we distribute the right keys to the right people, how do we store and back up and restore these keys, because even though that's something that cryptographers we generally don't like people to do, that is to take copies of keys, but it's something that's required by a whole bunch of industry legislation. How do we make sure that keys are being used according to the policy associated with them? So only the right people are allowed to sign with the right keys. How can we do auditing? How can we be sure that our audit trail of what cryptographic key was used for what is correct? How can we produce a report to convince some agency like PCI that we're really compliant with their cryptographic standard? How do we update and refresh these keys if there's been a compromise? Okay? So these are a whole bunch of pragmatic issues that typically fall out of the scope of a paper at Crypto, say, but are actually a real headache for somebody trying to manage a cryptographic system on a daily basis. And it is a real headache because crypto is now all over the place in enterprises. It used to be a rather specialist thing, but I got this thing. This is from an IBM presentation about where crypto is now used in enterprises, and essentially it's everywhere. So the things that you would obviously think of, like e-commerce and virtual private networks, obviously you're going to be using crypto there. But just about anything that's sensitive inside an organization now has some kind of cryptographic access control or encryption associated with it, partly because of things like Sarbanes-Oxley laws and various other regulations which are trying to make it harder for fraud to happen inside an organization. So now you essentially have to encrypt and cryptographically manage access control to everything. So managing keys for all of these different applications, all of which are physically located in different parts of your informatics system around your enterprise, is a massive headache, which has led to a trend towards trying to put all of your key management problems into one place. Okay? So how are we going to do that? Well, maybe we're going to use an HSM, one of these hardware security modules that I talked about yesterday, to manage the keys. And maybe we're going to associate that with a bunch of, say, smart cards or USB tokens that we're going to give to all of our staff, and that's going to go ahead.
Please I like to ask questions. Cut me off if it's ever inappropriate. The way you use the term API tweaks me a bit. Can you start over this by telling me what do you mean by security API in the context of your presentation? Just as a developer, I think of an API as a set of functions and libraries done, and I think you have a different definition, which is cool.
Right. So an API for me becomes a security API when you don't just want to allow anybody to call functionality through it, but you want it to enforce some security policy for you, right? So you want to be able to say, okay, I've got all these resources here, and I don't necessarily just want to give all these to the programmer. So I'm going to define the API in such a way that he can get the functionality he needs, but he doesn't get to access the secrets that I don't want him to have. Okay?
API, you mean things like get key secret or get or save key. When I think API, I think of individual functions.
I think that's really going to become clear if you just bear with me for about 7 or 8 more slides. It's going to become a lot clearer. Okay? And if it's not, interrupt me again. Okay?
You have 7
Deal?
slides of silence.
Very good. Excellent. Yeah, so there's this trend towards trying to put all of your key management into one place so that then you've only got one big thing to worry about. So Either you've got an HSM issuing USB cards, or increasingly big enterprises are trying to, people are trying to sell them servers which are going to provide them cryptography as a service over the network, which is going to do all of their key management chores for them and allow them to access the cryptography they need in some secure way. And indeed, the use of secure hardware for this kind of problem is actually a requirement in some industries, like in the banking industry. And each of these devices are going to have what we're going to call a security API, and I'm going to show some examples of that, which will hopefully make it clear what I mean. So the most common standard in use for managing access to crypto on a secure device, like a smart card or an HSM or a key server or whatever, is this standard defined by RSA. So there's a whole bunch of these things, public key cryptography standards, that are edited, so they're kind of curated by the RSA company, but the editor for each edition can be somebody working for anyone. The very first one just tells you how to do the RSA encryption algorithm, right? It tells you how to use certain padding modes and what have you. And there are a whole bunch of other standards, some of which have been merged or retired or what have you, that describe how to do password-based encryption and other kind of stuff. And the number 11 of the standard series describes an API for accessing crypto, which is called CryptoKey. The first version of it came out in 1995, and that's relevant because that design decisions that were taken then were obviously taken with the knowledge of crypto, which was contemporary in 1995, and that's influenced what is still remaining in the standard now. So that will become a bit more clear later on. And the current standard, the in-use version, is version 2.2, which still dates only from 2004. There is a version 2.3 in public draft at the moment, but it hasn't been adopted as the new standard. And if you want to browse it, there are lots of nice people who offer nice HTML interfaces to browse it online. It's a pretty big standard. It's about 400 pages of PDF to read. So how does PKCS 11 work? So the idea is that it's a standard that's going to offer interoperability to applications trying to get hold of crypto services, no matter what the underlying device is that's holding the keys and offering the crypto. Okay? So it doesn't tell you how you have to communicate from your PKCS 11 device, so your HSM or your smart card or whatever, and your host machine, so what kind of codes you need to be using on your USB smart card reader or whatever. It just tells you what application level services you're going to offer at the driver level. Okay? So if I'm going to give you a PKCS 11 device, if I say my device is PKCS 11 compatible, what I really mean is I'm going to give you the device and a driver. The driver is going to be able to talk to the device, and you can talk to my driver with the PKCS 11 standard. Okay? So then your application should work, no matter if you change between one smart card provider and another. I will say a little bit more about the communication between the driver and the device a little bit later if there's time. So it's a standard for, it's an API for the device, but at the application level. So I'm going to introduce a little bit of the jargon that's used inside PKCS 11 because this is going to be necessary to understand it. So a single PKCS 11 driver can offer several what are called slots to the application. Okay? So when I'm a PKCS 11 application, I want to get hold of some crypto, I might ask the driver, okay, how many slots have you got, and do you have a token inside those slots or not? And so physically, this may not correspond to the presence or absence of real physical devices. It's just an abstraction for communicating with the crypto services. I might quite easily, for example, have a single HSM that offers several different slots, each of which contains a separate install of different cryptographic keys and different functions. So when I've decided that the token that I want to talk to is really present in the slot of the driver I want to speak to, I ask the driver to open me a session with that particular token. Okay? So opening a session requires a PIN. So it may actually be a password, but it's always referred to as a PIN in the standard. And PKCS 11 supports two different profiles, so two different PINs for each token. There's a user PIN and a security officer PIN. So a user PIN can log in and actually call crypto services. The security officer PIN, he can't actually do very many things, but what he can do is set the user PIN, and that's really his main function. In more recent versions, they've been trying to add more functionality to the security officer, but we'll come back to that later. But for the context of the rest of this talk, just assume that it's going to be a user session that we're going to be opening with the device, and we're going to be just sending crypto commands to the device with the rights of a user. So PKCS 11 offers a sort of object model that allows you to access the devices on the token. And for each of these objects which is stored on the token, you can get access to these via what's called in the jargon a handle. Okay? So what is a handle? So you can think of a handle as just a pointer to the location in the secure memory of the device where the object is actually stored. Okay, it may not actually really be the physical location, but it's some identifier that tells the device where to look for that object. Okay? The important thing about a key handle is that knowing the value of the handle doesn't tell you anything about the value of the key. Okay, that's extremely important. So I can let anybody who logs into the device, I can tell him what all of the handles are which are currently in use and which ones of them have keys stored under them. And just knowing the value of that handle won't tell him anything about the real crypto value of the key. So it's okay for me to give that out. Then in addition to being accessed by these handles, keys have attributes. So what are attributes? You can think of them as metadata that's used to define the role of the key. Okay, so it's telling you what is the usage policy of this key. What am I allowed to do with it? What am I not allowed to do with it? What kind of key is it? So here's a little schematic showing a host machine and a trusted device. So if you were in the lecture yesterday, you remember that everything on the left-hand side, we assume that there might be an attacker here in the worst case. And on the right-hand side, we have a trusted bit of memory. We assume that we can't get physical access to that, and so that's where our secrets are stored. So here we have a device that's storing two keys, K1 and K2, and it's got handles N1 and N2. So these handles are available in the outside world. It's no problem for me to give them out to the host machine. And in addition to the keys, key 1 and K2, I'm also storing some of this metadata, these attributes, which are describing what is the policy, the usage policy of this key. And so I've just written A of N1 there. So that's some string of attributes, which is some booleans, some trues and falses, which is saying this key is available to do this, it's not available to do that. And we're going to see some more examples of exactly how that works. Okay, another little bit of jargon. So PKCS 11 talks about something called a key template. So a key template is a partial specification of these key attributes. So it may in fact be the improper subset of an entire specification of key attributes, but in general it may contain only a few of the attributes you need to define a key. And we're going to use these templates for creating and manipulating and searching for different objects on the device. Okay? So how does that work? Well, we construct an array of what are called, so I'm going to introduce some of the actual terminology from the standard here. So this little CK in this typewriter font, this is coming from the fact that this is a crypto key object. So everything that's an object in the standard is specified as a CK underscore something. So an array of these attributes, for which the order is unimportant, is a specification of a key template. So it's going to tell me something about the information of the attributes of the key that I'm interested in. Okay. So how do I use one of those? So if I want to call a command something like generate key, how do I do it? Well, I'm going to supply the device with a template, so a partial specification of the kind of key that I want. Okay. So typically I might say something like, oh, I need an RSA key, key pair, and I want it to be authorized for signature. Okay. So then I'm going to give a template which specifies the type of the key and maybe the key length, and then also says that the attribute for signature has to be set to true. And then my device is going to go ahead and process that, and it's going to make the key. So I've got a little bit of notation here. So I've written this kind of curly T to specify a template. And then in the course of processing this instruction, my device is going to generate a new value for a handle, which is this N, and it's going to generate a new value for the key using its key generation algorithm, and that's K. And where I've written H, N, K here, you should interpret that as being a predicate, which is saying, okay, in the mapping of handles to keys on my device, it's now the case that N is pointing to a key K. Okay? It's just a bit of shorthand for writing this. And then to the right, I've put a T, and this T is deliberately in a different font. Okay, that's not a typo, and that is because the template that you actually get when you ask the device to generate you a key won't necessarily be exactly the same one that you asked for. So there are two reasons for this. One of these is that you typically only partially specify the key that you want, and then the device goes ahead and adds some default attributes to the final template of the key that you actually get. But additionally, often implementations of PKCS 11 have taken their own decisions about what is a good template and what is a bad template. And devices that we've tested are liable to take the template that you give, change something about it, and then make you a key which doesn't correspond to what you actually asked for and give it back to you. So you need to be aware of this when you program with PKCS 11, in particular for the practical exercise a bit later. So what will happen when you ask for this template? Well, you might get back your handle, and then you know that your command has been successful. Or the device might refuse to do this, okay? So if you ask for something in the template which the device considers inconsistent, it will refuse to generate you a key. So you might, for example, have a device which doesn't allow you to make a key that can be used both for encryption and decryption and for signature and verification, although I haven't found one of those yet. Or you might get a message saying you haven't given enough specification in the template to tell me how I should generate the key. For example, you didn't tell me what length of key you wanted. But all of these things, exactly what error messages to give back in what situation here, are very underspecified in the standard. So every PKCS 11 device that you ever have to use, you'll find that it has a different set of rules for when it gives you back these error messages. Okay, so I've generated my key. I can also decide later that I want to change the attributes that I gave to that key. Okay? So I have a simple command for doing that. I give a template that specifies some new values for some attributes, and I give the handle of the existing key, and I'll get back a pointer to the same handle, but the result will be that I've changed the template, right? So this new T on the right-hand side of the arrow now contains some different sets of values for the attributes. But again, my device can refuse to do this. So certain attributes are read-only in the sense that once I've set them at creation time, the device won't let me change them again afterwards. And some attributes like that are very critical for security, as we'll see in a couple of slides' time. And then I have commands that allow me to share a key that I've generated with another device. And these are called the wrap and unwrap commands. So these are very simple. So I have some key on my device, Y2, and I want to share it with someone who has the long-term key Y1. And I've got handles for Y1 and Y2 on my device. And inside the attributes for the pointer X1, which is pointing to Y1, I have permission to do wrap. Okay, so this is another key attribute. This is saying I have the wrap permission on that key. And then for the key that I would like to share, so that's the key Y2, I've got a pointer to it which is X2, and I have the extract permission on X2. So that means this is a key which I'm allowed to take out of this device and share with another device. And so if I fire this command, the result is just that I'm going to get the key Y2 encrypted under the key Y1, and now I can take that away and introduce it to my other device. And then I introduce it there, and the guy already has his copy of, I've transposed the keys. That's kind of annoying, sorry about that. So anyway, the unwrap command works that if I have a pointer to a key Y2 and I receive a key Y1, and I have the unwrap permission on the pointer X2, I can specify the template that I would like to assign to the new key Y1, and then my device is going to generate me a fresh handle. It's going to assign that to the key Y1, and it's always going to set the extract permission to be true on the key that it receives. So this is something that's specified in the standard in order that you can track which keys are on your device that you made yourself and which keys are on your device that you receive from the outside world, because you might want to take different security decisions about what you do based on these attributes. But there's a whole bunch of reasons why these commands might not work. So you might find when you try and do unwrap that the key that you've wrapped doesn't decrypt to give something which I can accept and use as a key. Or it may be that when I try and call wrap, you point your handle at a key which doesn't have the wrap permission. There's a whole bunch of these different kind of errors that might happen, and so each of these devices will be set up to give these errors in slightly different circumstances. Okay, so just to understand that on our little schematic, so supposing I have these two keys, K1 and K2, and let's suppose, just for the sake of argument, that the only attribute set to true for K1 is the extractable permission, right, which is X. And the only attribute set to true for K2 is the wrap permission, which is the permission W. Well, then the only thing that the host machine should be able to get out of my device should be the encryption of the key K1 under the key K2, okay? So he can't do it the other way around because the attributes are not correct, right? So he can't extract K2 and he can't wrap using K1. So this should be the only thing he can get. And then I have commands which allow me to actually use those keys, so they're pretty simple. If I want to encrypt something under a key Y1, I have a pointer to it X1, I need to have the encrypt permission on X1, and then I give him my plaintext Y2, and I get Y2 under Y1. And then I have a similar decrypt command, and notice that the decrypt and encrypt permissions are separate permissions. All right, so that's enough to get a very basic idea for PKCS 11. So there are a whole bunch more commands. Some of them are very specific to operations you need to, for example, do little bits of the TLS protocol and things like this. But we've seen the core key management commands for the interface so far. So now we can think about what it means for an API to offer security properties, okay? So this API actually has a discussion in it, which is quite unusual, of what are the security properties that the API should enforce. So I said that the whole standard is about 400 pages. The security discussion is about a page and a half, so it's not exactly in depth. And it's written in a kind of committee-style English, which is a little bit hard to interpret, but let's try and work out what it's trying to say. So, point 1, access to private objects on the token and possibly to cryptographic functions and or certificates on the token as well requires a PIN. Okay, so we already knew that, right? We know that if we want to talk to a PKCS 11 device, we have to open a session with it. To open a session with it, we need to present the PIN. Okay, so that's fine. We understand how that works. Secondly, additional protection can be given to private keys and secret keys by marking them as sensitive or unextractable. So what does it mean to mark a key as sensitive? Well, there's an attribute sensitive, okay? And if I assign the attribute sensitive to a key and I set sensitive to true, that's what it means by marking a key as sensitive. Or unextractable, well, that's the same thing, except that I take the extractable attribute and I set it to false. So that's what it means by marking a key as unextractable. So sensitive keys cannot be revealed in plain text off the token, and unextractable keys cannot be revealed off the token even when encrypted. So you can sort of see that as a hierarchy, right? So these unextractable keys, they're my ones which rest permanently inside the device. They never come out even when they're encrypted. Then I have my sensitive keys, which are nonetheless extractable. So they're ones which I can't see the plain text outside, but I can encrypt them and share them with somebody else. And then I have my non-sensitive keys, which are ones anybody can see, okay? So they're not being protected except by the PIN. Now, they note in the security discussion that rogue applications and devices may also change the command sent to the cryptographic device to obtain services other than what the application requested. But they cannot compromise keys marked sensitive, since a key that is sensitive will always remain sensitive. So you remember I was saying that you can change the attributes of a key after you've created it, but certain attributes you can't change. They're read-only attributes. Once you've decided on the value for them, you can't change them later. So sensitive is one of those attributes, right? So if I create a key and I say this is a sensitive key, and then later on I say, okay, now set that key to be non-sensitive, the device is going to refuse. It's going to say that's a read-only attribute. You can't change it back to non-sensitive once you've set it to sensitive, okay? And similarly, a key which is unextractable, so it has extractable set to false, I can't later on decide I would like that key to become extractable, okay? So I call the setAttribute command and I say, please set this key extractable to true. The device is going to refuse. If it's respecting the standard, it's going to say, you're not allowed to do that. That's a read-only attribute. Okay, so now I have an idea of a security property. It should be the case that even if I'm a rogue application that's got access to the PIN and I'm able to call functions from the API, I shouldn't be able to get hold of the sensitive keys in the clear or the unextractable keys even encrypted. So now we can look at a PKCS 11 implementation and try and work out whether it really enforces these security properties. Okay, so we were looking at the example of key 1 and key 2, and now I'm going to say that key 1 is, in addition to having the attribute extractable set to true, he's also going to have the attribute sensitive set to true. Okay, so I've got a sensitive key, key 1 on the device, and I've got some wrapping key, K2, and I'm allowed to get key 1 encrypted under K2 outside the device. Okay, so far so good, because that respects the security policy. Okay, so my key K2 is not extractable, doesn't have X set to true. But I can't even get that outside the device, even encrypted, so that's fine. Key 1 is a sensitive key, and I can get that outside the device encrypted under another key. Well, that's also fine, that's allowed, because that key is extractable. So far, it seems like my implementation is respecting the policy. But suppose for a moment that key 2 also had the permission to decrypt ciphertext, okay? So now I'm allowed to use K2 to decrypt anything that I like. Well, this is bad news, right? Because now I've got a very, very simple attack, which appeared first in a paper by Jolly and Clulo at Ches in 2003. So in this attack, I very simply encrypt K1 under K2 using the wrap command, and then I call the decrypt command, giving the encryption of K1 under K2 as the input, and the device is going to just take that blob, decrypt it using the KK2, give me the result, and that's the result, key K1 in the clear, okay? Well, that's bad. That's not supposed to happen, because key 1 is a sensitive key. I'm not supposed to be able to get hold of that in the clear. But now it seems like I can, so that this is bad news. Okay, so just to, so I'm going to give the attacks in this kind of notation. So I'm just going to say what the intruder knows at the beginning. So the intruder knows the handles to key 1 and key 2. In the state, I've got that N2 and has got the permission for wrap and for decrypt, and N1 has got permission sensitive and extract. I'm just going to call the wrap command to get K1 under K2, and then the decrypt command on K1 encrypted with K2 to get K1 in the clear. Okay, well, that's obviously bad, right? And so we might expect that a good implementation of PKCS 11 wouldn't allow you to have wrap and decrypt set to permission on the same key. It seems like there's not really an application scenario where you'd want to do that, and it's clearly kind of dangerous. Okay, so what are we going to do inside the context of what we're allowed to change inside PKCS 11 to prevent you from being able to have a wrap and decrypt key on the device? Well, the first thing you might think is, well, we already reject certain templates. So I said that when someone asks me to generate a key or set an attribute on a key or create a new key using Unwrap, I can take that template and I can look at it and decide if I want to accept it or not. And I can say template inconsistent if I don't like it. Okay, well, that's fine. So let's add a rule which looks at this template and says, are you trying to set both wrap and decrypt using that template? And if you are, I'm going to give an error message and I'm going to refuse to do it. Okay. Well, then this should be the case now that you're not able to create yourself a key that can do both wrapping and decryption. So is this sufficient to prevent the attack? Well, unfortunately not. So imagine that we have some handle N2 pointing to a key that only has the permission to do wrap. Okay? So this is how I'm going to get around that rule with the templates and still be able to affect the attack. So first of all, I'm going to do the wrapping that I want to do to make my attack later. So I'm going to wrap key 1 under K2. Then I'm going to set the attribute wrap to false on the handle N2. Okay? Then I'm going to separately set the attribute decrypt to true. And notice that by doing that, I never broke the condition that I had a template on the device that had both wrap and decrypt at the same time. Okay? And now, of course, I can carry on with the attack because I've got my decrypt permission on my key. I can do exactly what I did before. I can decrypt this wrapped handle, and I can get hold of the sensitive key, K1 in the clear. So we're back to the same attack situation as before. Okay. What are we going to do about that? So we can introduce a set of attributes which, once they've been set, can't be unset, and ones which, once they're unset, can't be set. So notice that these already exist inside the PKCS 11 standard, right? So it's not we're not making a big radical change to the standard. For example, the CKA extractable attribute is already a sticky off attribute because once I've said that extractable is false, I'm not allowed to set extractable to true. And CK sensitive is the same, it's a sticky on attribute. Once it's been set to true, I'm not allowed to set it to false. So if I just add decrypt and wrap to the set of attributes which once you've set them on, you can't set them off again, that should prevent the previous attack, right? Because now I can't unset wrap and then reset decrypt again afterwards. Is this enough to prevent the attack? Okay, so now we're going to, like we did in the talk yesterday, we're going to try and use some formal techniques to work out whether the changes that we've made to the API are sufficient to put us back into a secure situation. So this is work that appears in a paper at CSF for about 5 years ago. And so I'm not going to go into all the formal details, but just to point out what the difference is between this and the models we looked at yesterday, the big difference is the state. Okay? So we have this global state, which is the set of attributes which are assigned to each key. And when I set the attributes on a key, they really do stay like that. And then if I do something, some more operations, and later on I come back to that key, it still has to have the attributes that I set earlier. And what's more, if I delete an attribute from the metadata of a particular key, then that really has been deleted. The operations that I can do now are not equal to the operations I can do earlier. And this minor detail means that a lot of the optimizations that would work inside our formal tools are no longer valid. They would lead us to get false attacks. So we have to have a slightly different approach to analyzing the problem. So in our model, we only include the attributes encrypt, decrypt, wrap, unwrap, sensitive, and extractable. In fact, there are about another 5 or 6 attributes doing things like signature and verify, but we don't include those for now. Right, so here's another slide with some stuff I'm probably not going to talk about in great detail, but just to say that in order to make this analysis tractable, we had to prove on paper that the attacker can't benefit from doing things, just like we did yesterday, doing things which seem a little bit crazy, like, let's say, encrypting a handle, or trying to use a handle as a key, or this kind of stuff. We have to prove that the attacker who only respects, we'll say, the type system of the API, is just as powerful as an attacker who doesn't respect it. So why do we have to do that? Just because if we allow the attacker to do things like encrypt nonces under handles and use handles as keys, the space of possible things he can do is so vast that we won't have any chance of exploring it using our model checker in a reasonable amount of time. So we do this little bit of work on paper. It's a similar kind of theorem and proof to yesterday, but I won't talk about it any more than that. Just to say that that proof exists, so that's why we're justified in only looking at these well-formed terms in the search for attacks. And it's quite tricky to write a model where we're allowed to specify templates, where templates are an arbitrary length list of attributes. That also makes for a big blow up in the model. So we set our attribute changing rules in a very simple way. We only allow you to change one attribute at a time. So you're allowed to set or unset any of the single attributes in the model. And then this gives us an easy way to include the modeling of the sticky on and sticky off attributes. So we just delete the rules that allow you to turn off a sticky on attribute, and we delete the rules that allow you to turn on a sticky off attribute. So we fixed the decrypt and wrap attack by adding sticky on attributes for decrypt and wrap. And we've forbidden you from creating explicitly a key which has both the permission to do decrypt and the permission to do wrap. Now we're going to ask our formal tool, our formal model checker, to tell us whether there is another attack. Yeah, so we've added these conflicts. So when you set wrap, well, I first of all check that wrap is off, but I also check that decrypt is off as well. And I do the same thing when you want to set decrypt. And that's enough in my model to prevent you from setting these two things on the same. But our model checker gives us another attack in this model. So in this particular one, we have an intruder who has the handles to two keys, key 1 and K2, and he also has his own key. So one thing we always do in this kind of analysis is that we assume the intruder is at least able to generate himself a bit string which is a convincing key, right? So it's just a key which starts outside the device. It isn't stored under a handle, but it's nevertheless a string that he can use as a key with the algorithm. So again, the N1 is a sensitive key and it has the extractable permission. But this time N2 is a key which has the permission to do unwrap and the permission to do encrypt. Okay? So what's the attacker going to do here? Well, he's going to take his key, K3, and he's going to encrypt it using the encrypt command of the API. Okay? So then he obtains a blob K3 encrypted under K2. Then he's going to ask to have that blob unwrapped using the same handle, N2, pointing to K2. So the device is going to generate a new handle, N3, that now points to the key K3 on the device. Then he's going to set the wrap permission to true on this key K3, and he's going to use that key K3 to wrap the sensitive key, the one we're going to attack, which is N1, K1. And so the result is that he gets K1 encrypted under K3. Well, that's bad news because the intruder, of course, he knows the value of K3 since it was his own key. He can decrypt using K3, the encryption of K1 under K3, and then he can obtain K1 in the clear. So we haven't used the decrypt operation at all, but we've still managed to get hold of a sensitive key in the clear at the end. So we've got another problem that we need to fix. So one thing we can do is to consider the fact that, well, in this case, the intruder was able to use the encrypt command and the unwrap command on a single key. And again, that seems like it's a conflict, right? Because just as decrypt and wrap, it was like, well, you were using a data processing command, the decryption command, and a key management command, the wrap command, on the same key. That seems like a bad idea. So here we've got a similar kind of problem. You're using a data processing command, which is encrypt, and a key management command, which is unwrap, on the same key, and that seems to be causing a problem. So perhaps we can add that to our list of conflicts as well. So we're going to add that as a conflict. And so what does the model checker tell us now? Well, now it finds another attack. So in this particular case, the attacker is going to essentially make himself two copies of the same key. And that's how he's going to end up making an attack. So he starts by setting wrap on a key K2, which is pointed to by N2, and then he's going to use N2 to wrap the key K2 with itself. So it's not really important that he wraps the key with itself, but I wanted to include this for a couple of reasons. One is to show you that a model checker, when it looks at a problem like this, often does things which a human wouldn't think of doing, because it's sort of dumb, right? It's just following the algorithm that's going to get it the shortest path to getting that key out in the clear. And so one of the things that makes this attack a little bit shorter is the fact that I only need to have one key. I wrap it under itself rather than generating another one, which would have taken another step. A lot of people, when they see this, they say, well, for a start, there's no way any real device is going to allow you to wrap a key under itself. Well, unfortunately, the truth of the matter is, yeah, pretty much all of the PKCS11 devices we've tested do allow you to wrap a key under itself. OK, then I'm going to set the unwrap permission on this key that I've got N2. And I'm going to unwrap the wrapping that I just made. So I'm unwrapping K2 encrypted under K2 using N2. And now I've got a new handle, N4, which is pointing to the same key, K2. Okay? So the important aspect of this attack is that I have two handles, N2 and N4, which both point to the same cryptographic value, stored in separate locations on my PKCS11 device. So this is another thing where people often see this and say, well, no real device will allow you to store the same key in different locations. It'll say that's the same key and put it in the same location. But that's not the case at all, in fact. All the devices we test, if you unwrap the same key again, you get a different location to store it in. Well, the important thing about this is that I have the wrap permission on the handle N2, and I can get myself the decrypt permission on the handle N4. So now I can still do the wrap decrypt attack, but I'm just using the keys stored in different locations, right? So I use the one stored in N2 to do the wrapping, the one in N4 to do the decryption, and I end up still getting out the key K1 in the clear at the end. So I can still go ahead and do the attack. And this is a real problem for the design of the API. And just in case we hadn't had enough attacks, let's have a few more. So there are more attacks where, for example, if I have a handle to a sensitive key and I can wrap it, and then when I unwrap it again, I can simply ask for a template where the sensitive attribute is set to false. Okay? So I'm going to get a second copy of the key. The first copy had sensitive as true. The second copy has sensitive as false. Well, if the sensitive attribute on a key is set to false, I have a command which will just allow me to read the value. Okay? So I can just run the getValue command and get hold of the key K1 in the clear. Much simpler than doing any of this wrapping and decrypting business. And this really works on a whole bunch of devices. And there are even more attacks. So another one is to the wrap with non-sensitive attack, as we call it. So suppose I have a handle to a sensitive key, and I have some non-sensitive key N2 K2. And then I'm going to ask to have my sensitive key wrapped with a non-sensitive key. Okay, well that's a really bad thing, obviously, because I can just ask for the value of the wrapping key K2, and now I can do my own decryption offline. I can decrypt K1, K2 and get hold of K1. And again, this is one of these things that we show and people say, but no real device will do that. In fact, lots of real devices do this. Okay, they sort of allow you to declassify your keys in this way. And there are even more problems. So the PKCS11 API supports a whole bunch of different cryptographic algorithms. You might have a key, a very long key that you've chosen to be resistant to quantum computing, and it's very big. But PKCS11, such as it's specified, won't prevent you from wrapping that key using a much weaker one, right? So now you've reduced the secrecy of that key to the secrecy of the wrapping key that might be much weaker, like a single DES key or something. It supports triple DES, but it allows you to split your encryptions of long triple DES keys in such a way that if it's under ECB mode, you can do clever tricks and recover the keys one at a time. And the unwrapping command, if you're using a encryption algorithm which is susceptible to chosen ciphertext attacks, often there really are real practical padding oracle attacks on the unwrap command when you're treating a sensitive key. And we'll look at that a little bit more detail in the practical in the afternoon. So I hope I've convinced you that there's a lot of problems with PKCS11 in its default configuration. Okay? Why is it so bad? Well, I guess one of the reasons it was written was really to promote interoperability, and clearly security wasn't the prime consideration when it was designed. And it was written at a time when our understanding of crypto was less good. Things like padding oracle attacks weren't really sort of common knowledge at the time, and so people hadn't really thought about that kind of stuff. So in the next half of the talk, I'm going to talk about how we can be saved. So how can we implement PKCS 11 in a better way so that we do end up with a secure setup? So there are various ways that this can be done, involving things like trusted keys, involving things like additional wrap formats, restricting the set of templates in other ways. I'm also going to talk very briefly, it depends whether I've got time left, probably there will be enough time, a little bit about the library that we use for programming PKCS 11. So this is especially important if you're going to come to the practical this afternoon, because that's what we're going to use to do some hacking experiments on some simulated PKCS 11 hardware. And I'm also going to talk a little bit and give a video demo of our analysis tool, which lets you take a PKCS 11 device and work out whether any of these attacks are present or not. Okay, so how are we going to fix PKCS 11? So there's one almost trivial way of fixing it, which is used, for example, in a lot of smart cards. So if I have a smart card, typically I don't really need it to do all of this clever wrapping and unwrapping and sharing keys technology. Often when I use a smart card, the only thing I really want to do with it is sign using the private half and give the public half to other people to use. Or decrypt using the private bit and give the public bit to somebody else. So I can just disable the wrapping and unwrapping commands, and I can pretty quickly arrive at a secure configuration. So that's not really a big deal. But there are other devices where I really do need to share all these keys, right? And I need to even make backups of private keys for various reasons. I might want to share private keys between several devices to get more throughput. So I really need to have these wrapping and unwrapping commands and all this kind of tricky stuff. So I need to do that in some kind of way that I'm not susceptible to these kind of attacks. So since we published that paper 5 years ago, quite a number of different propositions have appeared in the literature suggesting different ways that you can build these kind of interfaces, either following PKCS 11 or some other design, such that you're not susceptible to these kind of attacks. Some of them even have security proofs of one kind or another. As far as PKCS 11 goes, so after Jolyon's attacks were published in 2003, remember that I said that the latest version, version 2.2, dates from 2004, right? So 1 year after these attacks were largely considered. So it does include some mitigations, some measures that you can use to construct quite nice mitigations to these attacks. They were clearly rushed a little bit at the last minute. You can find that out because, in fact, the email exchanges of the list for PKCS 11 were public up until about 2005, and you can find them on an RSA webpage somewhere and see the people who are all saying, what the hell are we going to do about these attacks? Well, I think we should put this in. And so it's a little bit complicated to work out which ones of these measures are really necessary or sufficient for making a fix. The other problem is that if you go out to buy yourself a PKCS 11 device after this lecture, you'll find that there's actually very few of them around that support version 2.2, even though it's almost 10 years since that became the latest version. It's just that the lead time on these devices is very long, and yeah, if you're only looking at smart cards with very limited functionality, then perhaps it doesn't matter so much. Okay, so here's one of the fixes. So in PKCS 11 2.2, they introduced the idea of an unwrapped template. So the idea of this is that inside my template, I give a pointer to another template. And in that template, I give the assignments of attribute values that I want to give to any key which is unwrapped using the first template. Okay? So now I've got my unwrapping key, and it's set up here. And any key that arrives from the outside world, I'm going to unwrap it with this. And I already know what values to give that key when I create it on the device. I'm not going to listen to what the user asked for. I'm just going to give it the attributes which were in my unwrapped template. So that's very useful for getting rid of some of those rather trivial attacks that we looked at. So I could say that, well, this key is going to be used for unwrapping sensitive keys that arrive from the outside world. So I'm going to set in its unwrapped template that sensitive is true. So any key that arrives encrypted under this value is going to have sensitive true when it's stored on the device. And that way I don't have this unwrapped and non-sensitive attack anymore. Okay, that's great. It is a bit strange because you actually now have arbitrarily large templates, because you can give an unwrapped template inside the unwrapped template and another unwrapped template inside that unwrapped template, which is a bit curious. But anyway, forget about that. we actually are yet to find a device which supports this. So we've done a lot of experiments on a whole bunch of devices. Some of them have an unwrapped template field, but don't actually allow you to put anything in it. So we're yet to actually experiment with this. Another way that we could try and fix problems, so we saw that there were problems where we were able to wrap a key and then unwrap it again and give it a different template than its original one, right? So remember there was an attack where I first of all I had a wrap key, then I wrapped it and unwrapped it, and now when it came back I made it into a decrypt key, okay? So I was able to give to the second copy of the key a set of attributes different from its original set. That seems like a bad thing, a bad principle in general, right? So if I create a key with a particular set of attributes, that should be its attributes for life. I shouldn't be able to just manipulate them arbitrarily by wrapping and unwrapping. So how can we prevent this? Well, one way is that we can cryptographically bind the correct attributes to the encrypted key. And then when we receive the encrypted key to unwrap again, we can check this binding and make sure that we're giving the right attributes to the key that arrives. And so one manufacturer of HSMs, in fact I should say SafeNet now since they bought Ericom several years ago, already includes a particular method for doing this, a proprietary extension to the PKCS 11 standard. So what we would like to do then is take this countermeasure and show when it's working, when it's sufficient to give us a secure API. So how are we going to do that? Well, the first thing we're going to do is we're going to formalize the notion of an attribute policy. So that is the notion of what kind of keys you're allowed to create and how you're allowed to change the attributes of a key. So here's a quick summary of the commands that we've looked at in PKCS 11. Just for symmetric key, okay? So I've left out all of the asymmetric key versions. So we're allowed to generate keys, wrap and unwrap, encrypt and decrypt, and then we can change the key template using set and unset commands. So we're going to change that slightly. We're going to write them in the following way. We're going to say you can generate keys and you can unwrap keys. And we're going to use this predicate A to say that A is going to, essentially, it's like going to be a macro that's going to contain all of the sets of allowable attribute combinations which I can use in either the generate or the unwrap command, okay? And then in the set attribute value command, I'm allowed to transition from any set A1 of attributes to any set A2 of attributes. And so in this way, I'm going to define an attribute policy as a graph, okay? So the graph contains the set of allowable states for the object. So an object state is just a complete definition of all of the attributes, all of the trues or falses of the attributes that I'm interested in. And a transition relation which allows me to connect object states if I'm allowed to use set attributes and move between them, okay? So we're going to say that an attribute policy is complete if it consists of a collection of disjoint, disconnected cliques. And for each clique, we have this value that if there's the two attributes are in the clique, then their union is also in the clique. So this is going to make more sense if I just show you this simple picture. So here's a picture of a complete attribute policy. So where the letter occurs, that says that this attribute is true, and all of the other letters are assumed to be set to false. So I'm going to essentially divide my keys into the key management keys and the data processing keys. And the data processing keys are allowed to do encryption or decryption or both. And the key management keys are allowed to do wrapping or unwrapping or both, okay? But notice that there's no arrows joining these two cliques. That would be a bad thing because that would allow me to make some transition between a key that can do either wrapping or unwrapping and one that can do decryption and encryption. Yeah, and notice that I don't have, for example, I don't allow you to create a key that doesn't have any attributes at all and then decide later whether you want to make that into an unwrap key or an encrypt key. And the reason for that is because you might make a copy of the key at any time by doing wrapping and unwrapping. And if you could just make a copy of that none key, then later on you could move one of them into the unwrap state and one of them into the encrypt state, and then I'm done, right? I mean, now you can go ahead and make a whole bunch of attacks. So we're going to restrict ourselves to attribute policies that look something like this. Okay, so notice that each of those cliques had a sort of maximal point. It had a point which has the property that if I can, anything that I can do with any of the other nodes in that clique, I can definitely do with the endpoint node of the clique. So in this example, my endpoint nodes are the WU and the ED. So these are the endpoints of the policy. And we show on paper that if you can, any derivation, so that any sequence of commands in an API with a complete policy exists only if and only if there's a derivation in the API using just those endpoints, okay? So what I'm saying is the problem of proving this attribute policy secure is equivalent to the problem of proving the security for just where all I can do is make a key that can do either W and U or E and D, okay? So all of my keys now are either wrap and unwrap keys or encryption and decryption keys. And if I can show security there, that'll be sufficient to show security for this policy. Okay, so now we have the problem that we want to get ourselves a bounded model because we don't know how many keys of each type I'm typically going to want to create. And I want to put some bounds on this so that I can do my model checking in some small model and conclude security for an unbounded number of keys. So we're going to bound the number of fresh keys that you can generate to the number of different endpoints. In fact, what we're going to say is that every time you ask for a key of the attribute type wrap and unwrap, you're actually going to get the same key, okay? So this isn't something we're asking from the implementation. This is just an abstraction we're making in our model. And what we're saying is that if we can find, the problem of finding an attack in this model is equivalent to the problem of finding an attack in the real model where you get a different key every time. And then we're going to bound the number of handles to the square of the number of endpoints. So what we're saying is that a priori it might be possible to get a handle for each endpoint for each key. We don't know that we're going to be able to prevent you from getting a wrap and unwrap handle and an encrypt and decrypt handle for the same key. So we have to allow that number of handles in our model. And then we're going to give the intruder his own key as usual because we know that there are some attacks which rely on the intruder being able to play about with some key value of his own. So that gives us a bound on the total number of handles of EP plus 1 all squared. And that's very small for the typical kind of models that we're interested in. Okay, so here's the model that we're actually going to try and verify. So does this laser thing work? So I talked about Ericom having their own mechanism for binding the attributes to an encrypted key. So it actually is a little bit particular. It works like this. When I ask to do wrap, my device is going to generate itself a macking key, MK, and it's going to work out the HMAC using MK of the key, Y2, so this is the payload key, the one I'm wrapping, and the string of attributes, which is this twiddly A. And then it's also going to give me that MK, the MAC key, encrypted under Y1. So both the payload key, Y2, and the macking key, MK, are both going to be encrypted under Y1 in order to be sent around the network. And the idea is that when that arrives back to do an unwrapping, I'm going to first of all decrypt myself the macking key using the key Y2. I'm going to look at the attributes which the user is asking to set on this key. I'm going to create myself the MAC of the payload key, the attributes, and I'm going to use this XM. And if they match, only if they match, am I going to go ahead and generate the key and assign it the string of attributes that you asked for. Okay. So we're going to try and verify this configuration, and we're going to use the attribute policy that I was just talking about, where we have ED and WU as the endpoints. Okay. So what happens when we give this to our model checker? Well, first of all, we're going to define the properties that we want to check. So we're trying to work out whether, so we're going to assume that all the keys on the device are sensitive. And we want to work out whether the intruder can ever learn for himself the plaintext key K for a handle for which he has NK. Okay? So the first property we start with is that, okay, if the intruder starts with nothing, so he doesn't start with any known keys, then he can't obtain any known keys. So we're saying if you arrive, you try and attack the API, you don't know anything except the values of handles, there's no way that you can get the key value K out in the clear. Okay, that's good. And our model checker can blow away this kind of problem extremely quickly. So then we would like to prove a kind of robustness property, where we would like to say, okay, suppose that the intruder manages to get hold of some key, which I'm going to call it KI, which is an encryption and decryption key. Okay, so it's a data processing key. Maybe he got hold of that because, I don't know, some side channel attack on your little device or something like that. Maybe you're going to use this key quite a lot, so they might make it more vulnerable to side channel attacks. Well, we would like it to be the case that if you manage to get hold of an encryption and decryption key, that's it. You can't get hold of any more keys because all you should be able to do with this key is encrypt and decrypt data, right? You can't wrap any other keys on the device. So you should still be relatively safe at this point. But in fact, there's an attack that our model checker found. So I do a lot of this work where I analyze formal security problems in model checkers, and skeptical people quite rightly often say, well, you say that you found this attack doing your model checking approach, but I bet that it was, in fact, during the phase where you had to write down all the rules in a logical way and then you looked at it, you probably already saw the attack, right, before you even put it in the model checker. So this was a case where that really didn't happen, right? In fact, when my model checker showed me this attack, I thought I'd made an error in the model because I wasn't expecting there to be an attack here at all. So I spent a long time trying to debug the model and eventually had to conclude that, in fact, the attack was real. So it's a nice example of how just the fact that the model checker doesn't have your preconceptions about what really is a secure configuration and what isn't, you can really avoid making mistakes in this way. So how does the attack work? So we assume that we've lost a session key, so we've lost an encryption and decryption key. So the attacker has a handle NIKI, which points to the key KI, okay, which is the key that he's learned. And this handle NI has the encrypt and decrypt permissions. And somewhere else on the device is an encryption and decryption and a wrapping and unwrapping handle, okay? So what's he going to do? Well, first of all, he's going to ask to wrap an encryption and decryption key, specifically the one that he already knows the value of, okay? So he's going to ask to wrap that using the wrapping handle N2. So the result is that the device is going to give him his key KI encrypted under K2, the macking key K3 encrypted under K2, and KI with the attribute marker ED in an HMAC, telling you that that's one of the correct attributes for this key, okay? Now he's going to go ahead and ask to have this unwrapped. Only instead of presenting KI encrypted under K2 and K3 encrypted under K2, so K3 should be the MAC key, he's presenting 2 copies of KI encrypted under K2, okay? So in the place where he's supposed to be presenting the MAC key, he's actually presenting KI encrypted under K2. Now, since he knows the value of KI, he can make himself his own HMAC, which is an HMAC of KI, only instead of saying that KI is an ED key, he's saying that KI is a WU key, a wrapping and unwrapping key, okay? And of course, the device, when it comes to unwrap this, it's just going to say, well, fine, so first I should decrypt the key, I should decrypt the MAC key, now I should check that the MAC is correct for this value, yeah, that's correct, that's fine. So now I'm going to generate you a handle pointing to KI, but now this is a wrap and unwrap handle pointing to KI. So now I've managed to turn my encryption and decryption key into a wrapping and unwrapping key. And of course that's bad news because now I can use that handle to wrap any other key on the device, and since I know the value of KI, I'm able to decrypt that and get that in the clear. So I'm able to get hold of the rest of the keys which are on the device. So that's quite nice. There are various ways you can fix this, by the way. I'm not sure if I put that on the, yeah, so if you want to carry on using the ERICOM thing and you want to do it in a better way, you can, for example, put a copy of the wrapping key inside the HMAC, okay? But putting keys inside these MACs, this is the kind of thing which cryptographers tend to feel a little bit nervous about. So I wouldn't necessarily recommend this ERICOM solution as the best way to fix the API. But if you were doing this and you wanted it at least to get a security proof in your model checker, this would be the kind of manipulation that you could make. And if you do this, then our model checker will now verify this property. Okay, so there are other ways to fix the PKCS 11 standard. One of them is quite a strange fix where you end up having to use unidirectional symmetric key encryption. So I need to have, so I end up with a template which allows me to do encryption and unwrapping. And I have to have one symmetric key for talking to you, and you need to have your symmetric key for talking to me. So why is this interesting? This is only interesting if you really have got to use version 2.11 of the standard and you haven't got access to all these other nice ways of fixing PKCS 11. There is at least a way that you can do it, but it's a bit, let's say, the overhead is a bit heavy. If you have version 2.2, then you can use this mechanism called wrap with trusted. Okay, so a key which is marked as being wrapped with trusted can only be wrapped by a key which itself is marked trusted. So there are these 2 new attributes introduced in version 2.2, wrap with trusted and trusted. And the trusted attribute can only be set by the security officer. So the security officer has to log into the device using his separate PIN, and then he can fire a command saying mark this key as trusted. Then he logs out and then he's done. Okay? So this is okay, except that it means that if you want to introduce new trusted keys, you need to get your security officer to go and log into everybody's smart cards or everybody's devices, which you don't necessarily want to do. So it's not suitable for every situation. But it does at least give you a way to get hold of the security properties you'd like to have. And if you don't update your keys very often, then maybe this can be a good solution for you. And you can read more details about this in a couple of papers. And then you can, if you don't like any of these configurations and you want to find your own, you can use our tool.
Sorry to interrupt. Maybe I missed something, but could you have the security officer place a master key on the device and use that as a key encrypting key for subsequent updates?
So,
basically one level of indirection.
right, so if I'm right, which I might not be, you can't assign the trusted attribute through an unwrap operation. You can only assign it through the security officer login. But I'll check that.
Yeah.
So I think the idea is that you, yeah, right, so you only do this if you don't expect that you're going to update the keys very frequently. So you set up one trusted key, and then that's your long-term key, and then you only use that to receive new data keys, and then you're done. If you need one more level of hierarchy, you need the security officer login again. Yeah. Right, so supposing you don't like any of these configurations and you have your own and you want to know whether it's secure or not. And so we've been working on this device Tookan, this software which allows you to test some device and work out whether it's secure or not. So it works in a very simple way. It's going to take your PKCS 11 device and run a series of reverse engineering queries on it. So essentially what it's trying to do is, you've seen these slides where I was showing you, okay, this command might fail, it might give you this error message or not. What Tookan's going to try and do is for each of those commands work out what set of inputs will give an error message and what set of inputs will be allowed. Okay? So it's going to go through and do that for every command in the interface. And then from that set of trues and falses with these commands, it's going to generate a version of the formal model that you've been looking at and send that version of the model to the model checker. And if the model checker finds an attack, it'll try and execute it on the device. So I've got a little video. Oh yes, I should mention it's my wife who makes the logos, so I have to mention that every time. I've got a little video demo, hopefully. Don't know how legible that is. Probably not entirely legible, but maybe it doesn't matter too much. You're going to get the kind of basic idea of what's going on. So we're connecting our PKCS 11 device. Remember, we're always giving the PIN, right? So this is credentialed testing. We're already allowed to use the PIN. And now I'm going to hit, this is the sort of dummy mode where you run all the steps. And Tookan is now doing its reverse engineering process on the device. And if you look at the console, you can see what's going on. It's trying all these different kinds of templates, and it's getting sometimes an OK and sometimes an error message. And now in that way, it's learning what are the combinations of attributes which are allowed for each of these commands. So this will only take a few more seconds. Right, so in this case, we were able to find a variant of the wrap and decrypt attack. In fact, using the same key twice. So I said that you can often do this. You can encrypt a key under itself. And just for fun, Tookan will give you the output of the attack as a standalone C file. So you might want to be able to test this separately or send it to your manufacturer and say what's going on here. So it will automatically compile you a C file which runs and results in you getting the plain text. Okay, so that's the end of the little video. If you want to see more of that in the break or in the lunch break, then I'd be very happy to show you a bit more detail about exactly how Tookan generates its model and how it manages the different configurations. All right, so what happens when we use Tookan? So we did a case study with Tookan on a bunch of smart cards and USB authentication tokens. And here's a summary of some of the results in a little table. So everything in the top half is a smart card, is that right? No, everything in the top half is a USB token, and these things are all smart cards. And so what you can see very quickly from these results is that every device which can wrap sensitive keys, okay, every device which allows you to do that operation, also has an attack in this column, has some variant of wrap decrypt. So either you can wrap to a non-sensitive, or you can use a non-sensitive key to wrap, or you can put in your own key to wrap. Or Tookan managed to find some way of making that kind of attack work. So that's good. I mean, that sort of it makes us feel like our tool is working well. But then there's a sort of sad part of the story. So the sad part of the story is this column. So these are the devices for which, in fact, you can just read the sensitive keys anyway. Right? So you can just send a read command to the device, say, can I see the value of key 1? And instead of saying, no, you can't see key 1, that's a sensitive value, it actually just gives you the value of key 1. So you can imagine we made this nice model, we had this nice reverse engineering, the model checker and all this stuff, and then it was a bit sad when we found this, this kind of stuff. And that includes, for example, this RSA device, which costs $300 or something, or whatever. These ones are extremely cheap, sort of Hong Kong manufactured copies of the main, where is it? I haven't got it on there. The main Athena token, so maybe it's a little bit less surprising. But yeah, it's interesting that the Gemalto token, so version 1, not vulnerable to anything, upgrade to version 2, vulnerable to everything. Yeah. But I mean, so yeah, in the context of smart cards, not all of these attacks are really necessarily catastrophic, but at least shows you that our reverse engineering process is working well. Okay, so I'm just going to mention a little bit in preparation for the practical this afternoon, that I'm not going to dwell too long on this because some of you might not be interested in coming to the practical, that so programming in PKCS 11 directly is a real pain in the ass, basically, because you have to keep throwing things into buffers and taking them out again, and there's a lot of housekeeping going on, especially building up these structures that contain the templates and things, and you might not really want to be doing that in C. Maybe you're the kind of guy who loves doing that in C, in which case you don't need that kind of library. But a whole bunch of people have written libraries that allow you to program in PKCS 11 in some other language. So there's one developed at the University of Graz, there's ones in Python, there's all sorts. And so we developed one, for better or worse, it's in Java, as part of the Tookan project, and it has a C++ and a Java interface. And we're just going to have a look at a few quick examples of how you do this programming in Java for B. So here's an example of just opening a session with a PKCS 11 device. So I need to know in a string the location of the library that contains my PKCS 11 implementation, and I need to know the pin. And then I'm just going to ask to generate a new B object using that library and that pin, and this is a slot number. Okay, so in this case I'm looking for slot number 0. And then I have a whole bunch of methods I can call on this object B. So for example, I can call the getTokenInfo method, and this is corresponding to the getTokenInfo function in the PKCS 11 library, right? And so what we've done is we've mapped the majority of those PKCS 11 functions to methods in this library, and then you get it back in a nice way that you can print out the info for the token. Okay. Let's do something a bit more interesting. So we can, for example, look to find all the objects on the device. Okay, so here I'm using an empty template because I want to find all of the objects on the device. So this find function, this find objects function, is also a standard PKCS 11 construct, right? We're just using it here in our particular implementation. So if I give an empty template, it's going to tell me about all of the objects that it has. And so then I can tell you how many objects I managed to find. And then for all of my objects, I can go and tell you a little bit about them. So for example, for each object, I can do something like I can get the template, and then from that template, I can get the label. And typically in PKCS 11, we use these labels on keys as a sort of reminder of, what the hell was that key I created anyway? I meant my super secret encryption key or something like that. And notice that we have to, all of these kind of things we have to catch exceptions from, because often if the template's invalid or the object, sometimes the tokens report a object existing, but when you actually try and fetch it, there's nothing there, and you get an error message. So you're always having to put try-catch blocks around all of these P11 calls. So let's actually do something with a key. So here I'm going to try and generate a key. And I'm just going to generate a key, and all I'm going to say about the templates, I've made myself a new template here, and now I've got a bunch of methods to set the attributes on these in this template. And here I'm just setting the token attribute, okay? So there are two kinds of keys on P11 devices. There are token keys and session keys. Token keys are ones which will still be there next time you come back to the device. And a session key is one that will be erased when you close the session, okay? So if you want the key to be one that will still be there later, then you have to make sure you set the token attribute to be true. So now I'm just going to call this method to generate key, giving this particular template. And then later on I can say, well, okay, actually I would quite like to have the encryption permission on this template, so I can set encrypted true inside this template. And then I can call the set template. And notice I'm using the object handle that I got from generating this key here, and now I'm calling the set template method to add that template to it. Now I can use a key to do something, so here I am using it to do some wrapping and some encrypting. This is all not too exciting. What's interesting here? Oh, so something that you will need to remember later, so if you come to do the practical, is you have to set some things about what is the class of the object that you're about to receive when you're using Unwrapped. So you have to say, for example, this is going to be an ANS key and it's a class secret key. Of course, you've got all these code snippets on the handouts, right? So you can use them in the practical later. Okay. Enough of the code snippets. So just to talk about, to finish up, about, so maybe by now you're sort of sick of PKCS 11 and you're thinking, well, there's no way I'm going to use that for my secure application. That's crazy. So what are the chances of getting a replacement for P11, a better API with better security properties and easier to understand and so on? Well, so it's something we've been working on, and not just us. So with a collaborator, I presented an API at ESRX, which designed for an API with some security proofs, where you have certain features such as you have to fix the attributes at creation time. You're not allowed to switch attributes later on. And we have an interesting way of assigning attributes where you say what is the level of this key in a hierarchy, and you say which other agent identifiers should be allowed to have access to this key. And in a paper at CCS 2012, we extended this to key revocation. So what do you do if you find that no matter the fact that you're using secure hardware, somehow you've lost a key? How can you apply some revocation operations and have some security guarantee about the state of your device afterwards? And recently we've extended it from just symmetric to asymmetric crypto as well. And now a version of this API, so unfortunately we don't get to see the real API that's going to be implemented because it's a defense version. So I was involved in a collaboration with the French Ministry of Defense where I worked on an unclassified version of the API and they were working on a classified version, and there was a sort of very thin channel of exchange between the two of them. But they have essentially built for themselves a version of this API that they're going to have commissioned and used in their apparatus. So that's good. But we're not the only people doing that. So at the same time we presented our API in 2009, these guys from IBM presented a very, very different design. So they took the opposite extreme. They said, okay, you don't assign any attributes to your key when you create it, but as you use the key, I'm going to learn what the attributes of the key are, right? So if you use it to wrap another key, I'm going to learn now, well, that's a wrapping key. You're not allowed to use that for encryption and decryption, okay? Or if you use it to encrypt, then it's an encrypt-decrypt key and you can't use it for wrap. That's fine, although it does pose some centralization problems. So I can't distribute that API on a whole bunch of different tokens that can't communicate with each other, because my security decisions are taken on looking at the log of what's happened to each key. So imagine that I created a key on 2 devices and I used it to wrap on one device and I use it to decrypt on the other device. Well, you know, that's obviously a problem. So I need to have a centralized storage where they both share their usage history, which was fine for those guys because they were essentially running this API for an IBM product, which is a central key server, and you have an account on it, and then that's where you get your crypto from. And there's just one of those, or maybe 2, a redundant one, and they really do share their log, so you don't have the centralization problem. So these are sort of two, you can see these as two ends of the design spectrum for a secure API. One is the distributed version on tokens with a fixed attribute policy. The other is a big centralized one where I just look at the log. Maybe there's some interesting middle ground. Yeah, there's a couple of design points which come out of these, both of these APIs. So both of them use crypto to tie the attribute values of a key to its encrypted blob when it's being exported. Okay, so we've seen that that causes problems in PKCS 11. The fact that I can wrap a key and then import it as something else. Both of these designs, which came out at the same time, we obviously made the same decision that we need to prevent that, and the best way to do that is with some crypto mechanism. They both separate the roles of keys explicitly, so they don't allow you any way to generate a key which can do both wrapping and decryption or something like that. And of course, they specify more modern encryption schemes. So one of the problems with PKCS 11 is it was designed in a time essentially prior to people really understanding the need for authenticated encryption, and that leads to a lot of problems. The more modern proposals all define better requirements on the encryption schemes. So there are, as well as these academic proposals, there are people talking about better versions of key management APIs in industry. One of them is this OASIS KMIP consortium. So KMIP stands for Key Management Interoperability Protocol. So this is one of those things that sort of had waves of enthusiasm. So for a little while, everyone was really enthusiastic about it in about 2006, and then everyone became unenthusiastic again. But now recently, people have seemed to be more enthusiastic about it, and they're trying to push forward into a new version. So obviously, as researchers have been looking in this area, we would like to try and get some of our ideas into this standard, but it's not clear whether that will actually really happen. We'll watch this space. Okay, so just to summarize, so we've looked at RSA PKCS 11, which is the ubiquitous standard for APIs for key management devices. And we've seen that there are many, many attacks. So I'm not even sure how many there were in the talk, but probably this is the talk that I give that has the most attacks in it. And there are many different approaches that one might take to trying to make a secure version. So it's really quite a muddy picture. To try and clear things up, we've developed this Tookan tool, which allows you to automatically audit your PKCS 11 implementation. So this is currently being used by a major bank, and it's particularly useful for them because these bigger devices like HSMs that support PKCS 11, they support PKCS 11, but then behind the scenes there's a whole bunch of other configuration options that you can set. And it's not necessarily clear what the effect they're having on the access to the commands. And using something like Tookan, you can infer a model of what's really going on, and that can help you to make good decisions. We've had a quick look at our bees library, and we'll come back to that if you come to the practical this afternoon. Essentially what's going to happen in the practical is we're going to use bees to try and implement some of those attacks from the talk, and then some other ones which I haven't talked about quite so much. And I've mentioned that there are alternatives to PKCS 11 emerging in academia and even in some working groups in industry, but there isn't anything widely in use that's sort of ready to use right yet. Some further reading, so you can read the latest version of RSA PKCS 11 on the RSA website. You can look at the draft standard for version 2.3. You'll see that the draft version 2.3 does include some authenticated encryption mechanisms for symmetric key, which is an advance, but it doesn't yet specify, for example, a way to use those for the wrap command, which obviously would be really useful. I mentioned Jolyon's paper at CHES 2003. The basic work that we did with the model checker was in this CSF paper in 2008. And the paper that it shows you how Tookan works and gives you a bunch of the results was this one at CCS 2010. And the bit where we talk about how to reduce the verification problem for the unbounded model to this nice small bounded model was part of this WITS workshop paper in 2009. Okay, thank you.